Dr. A. Prasanna, working as Assistant Professor in the Department of Chemistry, V.V. Vanniyaperumal College for Women, Virudhunagar. In the last video, we have seen aromatic electrophilic substitution reactions, including nitration, sulfonation, Fiddlecraft's acylation, alkylation, etc. In that, benzene is getting substituted by an electrophile, leading to the product that is monosubstituted product. A detailed mechanistic notes we have seen in the last video. In this video, we are going to see the effect of substituent on further substitution, aromatic electrophilic substitution of monosubstituted benzene. So let me point out first how the monosubstituted benzene is formed. So that is we have seen in the last class, last video itself. That is benzene upon aromatic electrophilic substitution forms a monosubstituted product. Okay, so here all the positions in the benzene are equivalent. So we have expected that only one product is formed. Actually, one product is also formed. But when the monosubstituted benzene is subjected to aromatic electrophilic substitution, further, the remaining 5 positions are not at all equivalent. They are different. That is, the second and 6th positions are equivalent and they are said to be ortho position. The 3rd and 5th positions are equivalent and they are said to be meta position. The 4th position, that is said to be para. So, all the 5 positions in the monosubstituted product is not at all equivalent. So, it may lead to 3 different products. That is, it may lead to the substitution on monosubstituted benzene leads to 3 different products. That is, that may be ortho product, meta product or para product. Actually, what the exact products, that is the reaction proceeds to give ortho or meta or para products, that is predicted by the 2 influence effects, that is directive or orientation effect, that will decide which product is formed predominantly. Also, the second influence effect, that is activity effect, that decides the rate of the reaction. So, the rate of formation of ortho product is maximum or any other product is possible, that is predicted by activity effect. So, there are 2 different effects, that is directive or orientation effect and the activity effect that decides the nature of the product. Let me focus first the directive effects of the substituent. In benzene, already I have pointed out all the positions are equivalent, but in monosubstituted benzene, the 5 remaining positions are not at all equivalent. So, upon viewing 2 ortho positions are possible, so we may expect 40% of the ortho product and 2 meta positions are possible. So, we can say 40% of meta products may be possible and only 1 para position is there, leading to 20% of the para product. So, upon on a statistical basis, this may be expected, but this not actually happened. So, actually, the nature of the product, the percentage of the product formed, that depends upon the nature of the first substituent on the ring rather than any mathematical statistic. The directive influence is studied under 2 different effects, that is ortho-para directing effect and the meta-directing effect. Let me point out first the ortho-para directing effect. Okay, there are certain substituents which direct the second substituent on further aromatic electrophilic substitution to the ortho and para positions simultaneously. So such substituents are said to be ortho-para directors. Let me point out the example. Let us take this phenol. So this is the monosubstituted form, that is a monosubstituted form of benzene, that is in benzene OH group is there. Okay, this phenol is further nitrated. So we may expect 3 different products. So actually we got only ortho and para nitrophenol in 53% and 47%. The meta product is 0%, that is it's not at all formed there. So this OH, the first substituent in phenol, that is hydroxyl group, that hydroxyl group directs the incoming electrophile of nitration, that is NO2 plus, to ortho and the para position. So we are getting orthonitrophenol and paranitrophenol. The metanitro product is not at all formed. So exclusively we can say this hydroxyl group is ortho-para director. Let me point out the other ortho-para directing groups, that is halogens. Chlorine, bromine, this hydroxyl group already we have seen. Amino group, that is aniline. In aniline, NH2 group, that also directs the second substituent to the ortho and para positions rather than the meta position. Methoxy group, methoxy groups that is not mentioned in this slide, but that OCH3 group, methoxy group is also ortho-para directing group. Okay, this ethyl group. So these are all the other ortho-para directing groups. Okay, let me switch over to meta directing effect. So for this I am going to take the example nitrobenzene. In nitrobenzene, the first substituent already present is NO2 group. This nitrobenzene, when it is nitrated further, the incoming NO2 plus group is directed to the meta position rather than the other ortho and para positions. Look at this. This meta dinitrobenzene is formed in 94%. This ortho and para, that is only in trace amounts they are formed. Okay, so this nitro group, the first substituent in nitrobenzene is nitro group. That nitro group is meta director. Let me point out some other meta directing groups, that is sulfonic acid group, cyano group, nitro already we have seen, aldehyde. So when we take benzaldehyde and this is subjected to further aromatic electrophilic substitution, meta product is expected exclusively. Okay, also acid functional group. These are all the other meta directing groups. Okay, this is the slide which recall all the ortho-para directing and meta directing groups. Okay, halogens, hydroxyl group, alkoxy, amino, alkyl. These are all the groups which directs the second incoming group to the ortho-para positions, whereas this nitro, sulfonic acid, these are all the groups which direct the second incoming group to the meta position. Next effect, that is activity effect, which decides the reactivity of the reaction. Okay, for this let me point out the two examples. That is, you take toluene. In toluene, the first substituent present in benzene is CH3. So what is the formula for toluene? In benzene ring, CH3 group is there. So that is toluene. So when this toluene is subjected to nitration, the incoming NO2 plus group, it takes up the ortho and para position, that is ortho-para directing group. When we look at this reaction reactivity, that is rate of the reaction, toluene reacts more faster than benzene. You compare the nitration of benzene as well as the nitration of toluene. When we compare, the nitration of toluene is faster than the nitration of benzene. So we have to look into that, why this actually happens. Okay. Also, look at this chlorobenzene. Even though chlorobenzene is orthopara directing, this chlorobenzene upon nitration, it forms the product in the slower rate compared to the benzene. For the second example, that is, we have to look into the reactions of nitration of benzene as well as nitration of chlorobenzene. When we look into that two examples, chlorobenzene is nitrated 30 times less than that of the benzene. So the reason is that activity effect. So activity effect operates here. So let me see one by one. Okay, so actually in toluene, that methyl group activates the ring for the nitration, whereas in chlorobenzene, the first substituent chlorine deactivates the benzene ring for the further nitration. That is the actual fact. Okay, so what is that activation and deactivation? What does it mean in the benzene ring? So that is we are going to see in the upcoming slides. Okay. So let us point out the activating and deactivating substituents. A substituent which activates the ring, that is benzene ring, for further substitution, that is said to be activating substituent or ring activator. When in the slide, look at the center, benzene is at the center. On the left side, we have what is that? Aniline. In the aniline, the first substituent is amino group. So this amino group is orthopara directing and it is the ring activating group. What is that ring activating? That nitrogen has lone pair of electrons on the on its atom. That lone pair of electrons that may be flow towards the benzene ring, which activates the ring for the further nitration. Okay, whereas in the nitro group, nitro group, that is the direct attachment of the nitro group to that benzene ring is nitrogen, that's electronegative in nature. This in further attached to a more electronegative atom, oxygen. Okay, so this nitrogen is more and more electron deficient in nature and it attracts the electrons from the benzene ring towards the nitro group. Okay, so the electron flows from the benzene ring towards the nitro group. So that is deactivation. So what is activation? If the substituent releases electrons towards the benzene ring, that is said to be activation of the ring. If the substituent attracts or withdraws electrons from the benzene ring towards that substituent, then that is said to be deactivation of the benzene ring. Okay, so if the activation of the ring has happened, then that rate will be faster. If the activation is not there, that is deactivated, then that substrate is said to be less liable for the further substitution. That is the meaning there. So when we recall the effect of substituent on reactivity, in general we can say orthopara directors or ring activating. That's not the fact. So when we look into this slide, look at the first three examples, that is hydroxy, methoxy, aniline, and aniline substituted, amino substituted products, alkyl substituted products, N-alkyl products, then methyl, alkyl, these are all alkyl substituents. Look at the fourth examples, that is fluorine, chlorine, bromine, iron, that is halogens. That halogens are orthopara directing. Okay, if this is the first substituent, then it will direct the incoming electrophile to the orthopara positions. But it is said to be ring deactivator. Okay, if the first substituent on the benzene ring is halogen, it is deactivating groups. So it is less liable for further aromatic substitution. That is the meaning. Okay. So meta-directing. In the meta-directing, this NO2, aldehyde, CO, or these are all the groups which strongly deactivate the ring for further substitution.